Everyone, we're going to start solving this May 2023 question paper. So let's start. This is Physics Unit 1. Moving on to the question paper. Now, obviously, as we already know by now that for Physics Unit 1, they divide the entire question paper into two sections. So we'll first solve section A and then move on to section B. Section B are the theoretical ones and section A only contains the MCQ. I always advise start from the serial the question is arranged. Question papers are arranged. For example, start from one and then move on to solving the question paper serially. If you get stuck, then yeah, leave that, move on to the next one, come back to that stuck question again after you're done solving all the questions. But don't start from section B and then think of solving section A at the end. Okay, so whatever, we'll start with question 1. Which of the following is a vector quantity? Efficiency is more like a percentage, right? Or ratio. So it's not entirely a quantity, vector or scalar. You can also obviously consider that as a scalar because it only has magnitude and not direction. So obviously this is scalar. Kinetic energy, any type of energy is scalar. Power is energy over time, where energy is scalar, time is scalar. So their like division of these two quantities will eventually produce a scalar quantity. So C is also scalar. Weight over here is a force, so which is obviously a vector quantity, which means D is the correct answer for it. The wind exerts a force of 225 Newton on a windsurfer. The windsurfer moves at a distance of 450 at an angle of 40 degree to the wind as shown. Which of the following expressions could gives the work done in joules on the windsurfer? Okay. In order to find out the work done over here, we obviously have to use the distance that is parallel with the force component which is parallel with this 450 distance, right? Again, the 225 Newton was actually the force exerted by the windsurfer, right? Sorry, the wind exerts a force of this much on the windsurfer. Yeah, right. Sorry, I was wrong. The wind actually exerts this force onto the windsurfer. So obviously, because of this force is not actually acting perpendicular or parallel to the direction of the travel of the windsurfer. So now only a component of it will work because even after this. 225 Newton being exerted on the windsurfer continue to travel along this way, right? Which means that the overall direction of travel is over here. So you're supposed to find out any force that acts along this plane, which is 20 to 25 cos 40, horizontal component of this force exerted by the wind. So in order to find out the work done, right, we need to find out the work done, which is force into distance. Force over here is 225 cos 40 multiplied with distance was 450. If you rearrange it, 225 multiplied with 450 multiplied with cos 40, this is how the equation would look like, right? Option B. Okay. Moving on to question 3. A student applies a force onto a copper wire. Which row of the table shows the length and diameter of wire that would produce the greatest extension? Okay. So for since they're not only like directing it with length, they're also directing with the extension also. So you have to use this equation, Young modulus over stress. Young modulus is equals to stress over strain. Now again, stress can be broken down into force over area, which is basically pi r square. I'm considering this is a circular cross section, divided by extension is strain is extension over original length. So if you just rearrange it, this is how the equation would look like. Mm, for pi r square, which is basically delta x is equals to FL Young modulus pi r square. Okay, yeah. So as we can see, x is actually directly proportional to your extension length, and radius is inversely proportional to extension. So in this situation, you are supposed to have a smaller radius, right, and a larger length, because extension directly proportional to length, whereas extension inversely proportional to radius, right? So smaller radius, larger length. In that case, only option C is the correct answer. As you can see, 2x means larger length and D means the original length or at least smaller length, right? Whereas they doesn't have any change in length. It has more radius. It has again more radius. So these are all wrong options. Only C is the correct answer. So question 4, a force extension graph for a spring is shown over here. Which of the following gives the work done in joules to extend the spring by 0.3 meters from its original length? Okay, so obviously at original length the extension is 0. So this is where the original length is actually. And for the extension at 0.3, this is where 0.3 is. We need to find out the force at this point. So if you go along this line, this is where the force is, that is approximately 2.6 as we can see in the graph. So this is 2.6 over here. So since we're trying to find out the work done for force extension graph, the area under the graph is always the work done. As you can see, this clearly creates a right angle triangle. So the area would be half base into height, where height is 2.6 as we can clearly see, and base is 0.3. So it is going to be 0.5, 0.3 and 2.6 all multiplied together, which is approximately option B, right? Like for me, I thought it was yeah, actually I was wrong. It was actually connecting at the 0.5, so we should have actually used this as 0.5 over here, right? So yeah, then that's it. 0.5 is the height over here. Okay, and we're using the equation work done is equals to half force into delta x, or extension over here. So yeah, that is it for question 4. I hope it was clear. Moving on to the next part. Two forces form a Newton's third law pair. Which of the following statement is not correct? So we need to find out the wrong statement. The forces act on the same object. This is actually for Newton's first law pair, okay, or for any kind of pair to be Newton's first law. This was a statement. This was a requirement that the forces must act on the same object. For third law, the statement was the forces must act on two different objects. So obviously this is the first wrong statement. All the other statements are right. They must have the same magnitude, they must act for the same time, and they must be of the same type. So yeah, all the three are correct. Only the same object in one is wrong. A student determined the acceleration free fall of G. She measured the time for a ball bearing to fall from rest, initial velocity 0, and a distance of s. She repeated this for a range of values of distance s, which row of the table shows a graph that would give a gradient equivalent to G. Okay, so as obviously we can understand that anything that she measured was distance and time over here, and she literally doesn't have the value for final velocity. So out of all the equations of motion, she can only use s equals to ut plus half at square, and it's quite easy also because the initial velocity was 0, so this entire product will be 0. So she's left with s half a t square, where you can obviously rearrange it like this: 2s equals to a t square plus 0, which is completely in the form of y is equals to mx plus c. Right, as you can see that x-axis you have t square, at y-axis you have 2s, and the gradient is equivalent to acceleration. So obviously you have to plot a graph of 2s over t square, and that will give you the value for your acceleration. So in that case, option B becomes your correct answer, right? On the y-axis, you have 2s. On the x-axis, you have t square. Okay, so moving on to question 7. A car travels with a velocity of 3. So this is certainly the value for your initial velocity. The car accelerates uniformly. So that means we can use all the equations of motion. So equations of motions are open to use. They move in a straight line with a distance of 15, and the final velocity of the car is 5. Which of the following expressions give the acceleration? So you have value for s, value for u, value for v. In that case, you have to use the equation v square u square plus 2as. If you make if you make acceleration the subject, in that case you're supposed to end up with v square, which was 5 square minus 3 square initial velocity square over 2 into 15. If you look at it, then this is exactly option D for you, right? V, U, and S. So option D is the correct answer. This was it for question 7. We'll move on to question 8. An object accelerates from rest, so initial velocity is 0, down a frictionless slope, which means that there are no friction, so friction is 0 Newton, and the object moves a distance of 20 meter, and the slope is at an angle of 23 degree to the horizontal as shown. Which of the following gives the final speed of the object in meters per second? Okay, the final speed of the object in meters per second, which is basically at this part, right? Over here, the oxygen is like the object is falling down. That means at the very initial stage, it only has this height above the ground, right? That means obviously at the very initial stage, it has gravitational potential energy, and at the final stage, it has this velocity, which indicates that at the final stage, it has this kinetic energy. So from this gravitational potential energy, this kinetic energy was made or converted, right? So we can use this equation mgh is equals to half mv square. The masses gets cancelled out, and finally you're left out with 2gh under a root. Obviously the height was given to you, which was sorry, the height was not given to you. You can calculate it using Pythagoras theorem. I can draw a very simplified diagram of a triangle out of this length was 20 and this angle is 23, and obviously it is creating 90 degree over here, so that means we can use opposite and hypotenuse, which is sine, and the opposite over here is height, so height will be equal to 20 sine 23 degrees, and eventually you can now write 2g is 9.81 in physics and 20 sine 23, everything under a root, right? So if you try to match the answer with any of the options that is provided to you can see 2, that's G, and that's 20 sine 23, right? So obviously option C is the correct answer. That's 2, this is G, and this is S sine theta. So yeah, option C is the correct answer over here. Moving on to question 9, a ball bearing falls at terminal velocity, which means all the forces are balanced over here, right? That's why the object was falling with terminal velocity. So we can write that resultant force over here is 0. Also, acceleration should be 0 over here. Through a liquid, the temperature of the liquid increases. If the temperature of the liquid increases with this increase in temperature, its viscosity is supposed to increase. So we can also write that viscosity will also increase since they are directly proportional. And the ball bearing falls with a greater terminal velocity. Okay, so it's not indicating that it is accelerating. It is still falling with constant velocity, but at a higher magnitude. Which row of the table is correct for the temperature of the liquid which row of the table is correct as the temperature of the liquid increases for the viscosity and for the viscous drag over here? Okay, we actually like for example, like what is actually happening is that obviously viscosity of the liquid increases for sorry decreases, right? For like higher temperature, viscosity will decrease. Oh wait, sorry, I actually made a mistake over here. For as the temperature of the liquid increases, viscosity should decrease, right? Because they're inversely proportional. Really sorry, they are inversely proportional, right? So if temperature increases, so viscosity must decrease. So in that case, only option B, like the correct answer should be from option B or from option D, right? In this situation, the viscosity decreases. So we need to identify now if the viscous drag on the ball bearing remain constant or it increases over this entire journey. Um, as the object was still falling with like as it was still falling with terminal velocity, that means all the forces should still be at constant, right? Since what is actually occurring over here is weight acts downward and drag acts upward, right? So since doesn't matter if the viscosity changes, weight will not change. So if weight doesn't changes, the drag force cannot also change. So obviously they must be at the same magnitude. The forces will just remain the same. It's just that now the fluid has less resistance within itself. That's why it can now fall at a higher magnitude. Other than that, the forces will remain like it was. So in that case, drag force would remain constant and viscosity is supposed to decrease. So option B is the correct answer for it. Moving on to question 10. Two identical springs arranged in series. Force A is 45 Newton. So a force of 45 Newton is applied to the springs as shown. The springs extended to a total distance of 15 millimeter. Total distance means that by together, like that means each spring is extending at 7.5 each. So which of the following expressions gives the stiffness of each string in Newton millimeter? Okay. Now, over here for stiffness, the equation was F equals to K delta X. Now, in this situation, as they're connected in series, and as we are also provided the total extension, not just a separate extension of each wire, we have to consider it like this, that since there are in total two forces, right? Since there are overall in total two forces, we have to consider it like in this part, that the total force was actually, how would I express it? For example, the extension for each of this situation will be half, right? For one spring. For example, F equals to K delta X over 2. This is delta X for you, right? Delta X over 2 for one spring. In that case, you can just take that 2 to the right hand side, or just make K the subject of this equation. So in order to do that, it will be K delta X, and eventually for K this is going to be 2F over delta X, right? At finally you have 2 multiplied with 45 over 15, and that's how you get Newton per millimeter, which is completely option D over here. Right, for series, the extension was given you as a whole, right? So if you have to find out the force or spring constant for just one of the springs, you have to divide the extension by 2, because this was the extension for both the springs who extended equally by 7.5, 7.5 each. So they just wanted to find an expression, so we found an expression for spring constant. So this was it for question 10. I hope it was clear. With this, our section A ends. We'll move on to section B. A rock falls from rest through the small distance s to the surface of Mars. The rock hits the Mars with velocity vm. And another rock falls from rest another distance through distance s. They have both traveled the same distance to the surface of Earth and hits the Earth with a velocity of ve. Calculate the ratio of vm over ve, and acceleration due to gravity on Mars is 0.38 g. Okay, so let's first find out that since we're trying to find out the final velocity, right? Vm, ve are actually the final velocities on Mars and Earth. So we can actually write expressions in terms of Mars. So for vm, that's going to be like for example for v square is going to be 0 square plus 2, g is 0.38 g s, right? So this is for expression for the like vm square. You get 2s, or actually 2 0.38 g s, right? This is what you get. For ve again, we're using the same equation. That's going to be 0 square plus 2gs, which is just 2gs over here. But finally, since you are trying to find out the ratio, you use this Vm over Ve, both with a square, because they had separate squares, right? We can use the basics indices rule of mathematics, and you can write it like this. And in the right hand side, you have 2 0.38 g s over 2 g s, which means it clearly shows that 2 will be cancelled out, g will be cancelled out, s will be cancelled out. At the end, you're only left out with Vm over Ve. Everything under a square is equal to 0.38. At the end, if you take that square from the left hand side to the right hand side, you end up with Vm over Ve. Since you have square on the left hand, if you shift it to the right hand side, it will be square root. So over here you get 0.38. If you calculate it, the ratio of velocity from Mars to Earth, that would be 0.62 almost. So you can just write this answer in this space over here. If you do not write it in the space, then you will be penalized 1 mark. Another thing, no need to write any unit. Never write a unit for a ratio. This is a ratio, right? So there will be no unit for this kind of maths. So yeah, we're done. Another thing, if you guys are troubling, like facing some trouble finding on the equation that I used over here, this is the equation for v square u square plus 2a is. So just write it down. Okay, so we'll move on to question 12. A man dives with sorry, from a platform into a swimming pool. The platform is 12 meter above the water surface as shown. Okay, the graph shows the vertical displacement of the man from the water surface after leaving the platform. Okay, so like basically the distance traveled in the air and inside the water surface after the man has jumped from that platform. So this is how the diagram would look like. State how the graph shows the man's initial vertical velocity is 0. Okay, so if I go there, initially, if you draw a gradient at this point, right, that will be an entirely horizontal line. And on a graph, the gradient of a horizontal line is always 0. For displacement time graph, the gradient is velocity. So obviously, at the initial point, the vertical velocity will be 0 because the gradient, as you can see, is 0 for velocity time graph, displacement time graph. So we can write that at the start or initially the gradient is 0, and we can calculate it by drawing a tangent at t equals to 0, which indicates that velocity will be 0, right? We can draw a tangent at t equals to 0 and calculate the gradient there, that is 0, indicating velocity is 0. Okay, so determine the vertical velocity of the man as he enters the water. So if I move on to this page, at 1.5 we can see the man enters the water. So you can draw a tangent over here because you can clearly see this is not entirely a straight line. So I would suggest draw a tangent, or you can just focus on this part of the graph. I'll highlight the section. Okay. It's a very small part of the graph that is quite linear, so I'm just using that part. Okay, no, sorry, not that also, just this part also. Right, so this is one point and this is the end point over here. So you can see that over here the x-axis was almost 1.4 and another x-axis is 1.6. Y-axis is if this is 5, in that case this is 1.5 to, yeah, this is 1.5, and over here this is 1, -1, right? So basically if you have to draw, like find out the gradient at this point, the like angle for this, oh, sorry, not angles, the coordinates for this is 1.4, 1.5, and coordinate for this is 1.6 minus 1, right? So 1.4, 1.5, 1.6 minus 1. Sorry for my cat. So we can find out the gradient. I'll do the gradient calculation over here. I already took the coordinates from that graph. So we have 1.4, 1.5, and 1.6 with -1. So if you have to find out the velocity, that will be -1 minus 1.5 over 1.6 and 1.4. So you get what? Minus 2.5. with 0.2, and if you calculate it, you can find out the velocity over here. Okay, which is approximately 12.5, like negative 12.5, but no need to get focused about that negative value, because this they just want you to find out the I mean, obviously it will be negative because it was in the downward direction, so you just want to find out the magnitude. No need to get concerned about the negative value that you have. So it will be 12.5 meters per second, right? This is it. Now then again, before entering the water, the man has a constant vertical acceleration. After entering the water, the man has a constant vertical deceleration. Draw the velocity time graph for the man as he enters for the man as he on the axis below. Okay, so we have to focus on this graph again. I can clearly see that at 1.5 the person or that surfer, or what was it actually, right, the man. Okay, so at exactly 1.5 second the man enters the water surface, which means that, and obviously they started at a certain height of almost what 10.2 meters above the ground, and they stopped at a distance of 4 meters inside the sea surface, right? So this was the distance over the entire course of journey, and we already know initially the velocity was zero, as we can see from the graph, right? It has a flat horizontal gradient at the very start, flat horizontal tangent whose gradient is going to be zero, so initial vertical component of the velocity was zero. We have to find out the final velocity with which the ball, not the ball actually, the person or the man actually hits the surface over here. So for that we have certain values that we have to use. For example, they have given you the value that traveled, which was 10.2. As you can see, this entire journey actually takes 1.5 seconds and travels 10.2 meters from zero. This was an equation for constant acceleration, so we cannot use v equals to d by t, because for v equals to d by t, the object must not accelerate. And over here, the question clearly stated that the object was accelerating indeed, right? So over here, we have to use the equation v square u square plus 2as, which means that now at this part, v would be 2a is 9.81 inside the water or above the water, velocity acceleration is 9.81, right? And s is 10.2, everything under a root. So if you calculate it, you get v equals to 14.4 meters per second. Okay, so this is what approximately the value is. You also calculated it over here, but this was kind of graphical method, so I would suggest always calculate it and then carry it forward, because that way it's much more accurate. So you get 14.14, or you could just stick to 14. So that way you're supposed to get, this is 11, this is 14. Sorry, over here there will be a point, right? Because the time was 1.5 seconds. Another thing, as it was traveling in the downward direction, in the downward direction, so um, with constant velocity, so constant acceleration, that means the graphs will be a straight line. One thing that in the downward direction, obviously the acceleration is positive, but okay, so as it was traveling in the downward direction, velocity is negative. So over here, your velocity is actually going to travel in the negative direction from 0 to this 14, and then again it will travel in the inside the water. It's actually decelerating, right? So for deceleration, this is how your velocity will actually occur. I know this kind of looks like that the numbers over here is actually for negative basis. If you consider the number theory from mathematical views, that yes, are moving upward, which means that in the negative direction the values are increasing. But this type of velocity time graph doesn't actually follow your number theory. Okay, the negative axis, the negative signs only gives you an idea about the direction, and this tells you that the object is decelerating, its velocity is decreasing from 10, 14, like from 14 to 10, from 8 to 5, right? They just focus on the magnitude. The direction only indicates the negative sign only indicates the direction. So this was it question for question 12. I hope it was clear. Moving on to question 13. A high-speed train accelerates from rest along a straight horizontal track. The final speed of the train is 76, so this is v, and show that the useful work done to accelerate the train is about 2g joules, and mass of the train is also provided to you. Okay, so over here, since you had provided with what velocities, right? So obviously you have to use the equation half mv square over here. So which is energy is so kinetic energy is half 7.2 into 10 to the power 5 multiplied with 76 square. If you calculate this, you're supposed to end up with 2.08 into 10 to the power 9 joules, right? And G actually indicates that 2 into 10 to the power 9 joules. So we can obviously finally write it in terms of G, that is 2.1 G joules. Okay. Then again, the car accelerates for 180 seconds, and the train has an input power of 16 megawatt. 16 megawatt means that 16 into 10 to the power 6 watt, right? While accelerating, determine the work done against air resistance as as the train accelerates. Okay, so determine the work done against air resistance. This was actually all the energy which was provided to your train, right? Sorry, no wait. 2.1 G joules, and so this was actually the energy that was used by the train. So this is the useful energy, and some of the energy was obviously wasted in order to work against the work done, right? In order to move against the air resistance, in order to do work against the air resistance. So for that case, we cannot actually find that how much energy was invested to work against the air resistance. So what we can do is that we can find out the total energy, because the total input power is given, and we can also find out the energy using this time. So we can use the equation energy is equals to power into time, where power was given you as 16 into 10 to the power 6 multiplied with 180. Right, this is power into time. E equals to power into time. We're using this equation. You finally end up with 2.9 into 10 to the power 9 joules. So this was your like total power over here, or total energy over here. So in order to find out the work done against air resistance, always remember that total is equals to waste plus useful, right? You have that useful, which was 2.1, and you have the total now. So you can easily rearrange the equation and make the waste energy the subject. Waste energy is basically the one that is used to work against the air resistance. So we can write that energy against air resistance is basically 2.9 into 10 to the power 9, and then subtract it with 2.08 into 10 to the power 9. So you finally get 8 into 10 to the power 8 joules. So this is the energy that was used by the train to work done, to work against the air resistance. So 8 into 10 to the power 8 joules. So we are done with question 13. I hope it was clear. Moving on to question 14. A sportsman hits a ball with a bat. The ball leaves the bat at a speed of 37 at an angle of 53 degrees with the horizontal. So this is the u speed, and we need to calculate the distance traveled by that ball before returning to the height it was hit from. Okay, As we can see that if it returns to the height it was hit from, that means the vertical distance over here was obviously zero. At the maximum point, velocity is zero, right? Only the vertical component of the velocity will be zero. Horizontal component would still be same, 37 cos 53. But let's just write the vertical and horizontal component at first. This is 37 cos 53, and the vertical component will be 37 sine 53 degrees, right? Now over here we want to identify the horizontal distance, this much. If this is 1 point and this is 1 point, I'm just assuming this is point x and point y, so we have to find out the distance between these 2 points, or point x and y. So at this point the ball is returning to the height, yeah, okay, so just the distance between this part. So this is a part of horizontal motion, but for horizontal motion we need to have the value for time. So we'll find that time from the vertical motion, and then we'll use that time for the horizontal motion calculation, because in projectile motion the horizontal and vertical motion are independent of each other, so they both travel different scenarios at the same time. So we'll first start with vertical motion. For vertical motion I will use the equation s equals to ut plus half at square, because over here u is 0. As you can see that whatever the distance was moved up in the upward direction was also moved in the downward direction. So if s is positive in the upward direction, it is negative in the downward direction. So if you add these two together, you end up with 0, right? So total distance would be s minus s, that's 0. So that's why you end up with s being 0 for the vertical motion. For u it was 37 sine 53. So you get 37 sine 53t, and half a means what? 9.81 multiplied with half, which is 4.905. So we can write 4.905 t square. Again, one thing, this is actually a case for double motion. So over here, your value for a is negative, right? Because in double motion, object, like the overall sign for your acceleration is negative. So let's remember one thing again. For double motion, a is minus g. Okay. So now we'll move on. So I'll just rearrange it and write it like this: 4.905 t square 37 sine 53t equals to 0. So if you make t, like if you take 1t as a common, you just start factorizing it now. You get 4.905t. So one value for t is 0, which will not be considered as a value. So basically, if you make t the subject, it becomes 37 sine 53 over 4.905. So if you calculate it, you get 6.024 to be your time. So now using this value of time to the horizontal motion, for horizontal motion you can use the equation v equals to d by t, where d is unknown, and as we can understand that on horizontal motion object really doesn't accelerate, so the velocity is always same. It's going to be 37 cos 53 along the entire journey. So you can use 37 cos 53 degrees multiplied with time is 0.624. So you get 134.145 meter. But for your question, if you focus all the data that was provided, um, 37 and 53, they were in two significant figures, right? So that's why your answer should be in two significant figures, because always remember, answers cannot be more accurate the data that was provided in the question. Answers should be less accurate than the data that was provided in the question. And by accuracy, the higher the significant figures you're using, the higher the accuracy. So I know your calculated value for D is like 134.145, but I will not like keep all these data. We cannot even use three significant figure over here because the data that was used in the question was only two significant figures. So it's better to write your answer to either one significant figure or two significant figure. So I'll just choose two significant figure because that's quite more accurate, right? Because if I choose one significant figure, in that case I would have to write just like what 100, and that was very less compared to the actual data. So I'll just write 130 meter. So this was it for question 14. I hope it was clear for everyone. We'll move on to the next question. The diagram shows machine used to launch tennis ball in a horizontal direction. The machine is on a frictionless ground. Okay. Before a tennis ball is launched, the machine is stationary. Explain in terms of momentum why the machine starts to move as the ball is launched. Okay. In this case, as the like this ground is frictionless, that means no external force actually acts onto the system during this entire explosion is occurring, right? So as before the ball was kind of projected away from the machine, they were both at stationary. That means they're like what, momentum before collision was zero, right? Stationary means that momentum before collision for the entire system was zero. So momentum before collision was zero. PBC means momentum before collision. Okay. Now again, if we have to follow the principle of momentum, that was that momentum for an entire system before and after collision should be conserved. That means if the value for your momentum before collision was zero, after collision it also has to be zero. But as you can see that we are projecting the ball away from the machine, so the ball will obviously move with a certain velocity. If the ball is moving with a velocity according to the equation momentum equals to mass velocity, if it has a velocity, it will obviously have a mass, and then again it will have a momentum over here. So in order to cancel out the momentum of that so in order to like cancel out the momentum of the ball, the machine moves in the reverse direction. So at the end, what happens is that whatever the value for your momentum of the ball was, the machine will also regain the same amount of momentum but in the opposite direction. So they will have different signs and eventually they will get cancelled out. Another thing, their masses will be like a very important factor. Higher the mass, smaller the velocity, because they are inversely proportional, right? So in that case, the ball will obviously move at a higher velocity, whereas the machine will move back at a smaller velocity because it has a larger mass. Okay, so they just want 3 marks, not that much explanation is needed. In the question, they only want you to write it in terms of momentum, and they want you to explain that why the machine starts to move as the ball is launched. Okay, so we'll first like start with the fact that um, before the ball was launched, the machine is stationary. The machine is stationary, which means that momentum before collision is zero. Collision is zero. Now again, according to the principle of momentum, total momentum before collision should always be should always be equal to the total momentum after collision, right? So we can write that according to the principle of momentum, is equal to the total momentum after collision. So momentum, is equal to the total momentum after collision. So what can we write now? So machine and ball must have equal momentum but in opposite direction to cancel each other out, right? So last line would be that therefore machine and ball must have equal momentum. Therefore machine and ball must have equal momentum, but in different direction, but in opposite direction. To cancel each other out. Okay. So yeah, this was it for 15A. I hope it was clear. Let's move on to 15B. We need to calculate the velocity of the machine just after the ball is launched. That means the final velocity, and the velocity of the ball is given. Masses of ball and machine are provided. I'll just draw a very simple diagram. Before collision, both were kind of stuck together and they didn't have any velocity, right? So this is mass of machine, this is mass of ball, and their combined velocities or initial velocity was 0. After velocity, like after collision, the machine started to move in this direction with a velocity of v, whatever it is, and the ball started to move with a velocity of in this direction with a velocity of 4.5. Now I'm going to consider direction towards right as positive, so I'll write that taking direction towards right as positive. So in that case, taking direction towards right as positive. So over here, initial momentum, like obviously momentum before collision was 0. So we'll just write 0 over here. Or you can just break it down and write it in details that mass of that machine was 2.9 plus 0.056, as both have the combined velocity. So we'll just write 0 over here, because both were stationary before the collision, and after collision they start moving with different velocities. So it will be 2.9 with negative v plus 0.056 with 4.5. So that's basically 2.9 v equals to 0.056 multiplied with 4.5, and v is 0.056 multiplied with 4.5 divided by 2.9. So you finally get the velocity of your machine as 0.0869. Okay, so 0.0869 meters per second. Also, one thing that as we assume the direction towards right is positive, and we also assume that the object, this machine, would obviously move towards this right, so towards this left, right? And according to our assumption, that is correct. That's why we found our answer to be positive. If this came to be negative at the final stage, then it would just prove wrong, that our theory was wrong. Obviously, as it didn't came out to be negative. That means our theory is right. That means after the explosion, the machine did recoiled in the backward direction and moved towards left. So if we have to find out the velocity, so we can write that this much velocity in the left direction, right? So we can just write 0.0869 meters per second left. So this is it. This is the end for question 15. So we'll move on to the next question. A small spherical air bubble moves upwards in a glass of water. The drag force on the bubble can be calculated using Stokes' law. State the condition needed for Stokes' law to apply to the bubble. Okay. Um, since it's already provided that it has to be small and um, it has to be spherical. Other than that, what is the flow over here should be laminar, right? So we can write that flow must be laminar. The bubble moves up at a constant velocity. The volume of the bubble is this much. We need to show that the upthrust of the bubble is about this much when the density is given. Okay, volume of the bubble. Okay, upthrust. So yeah, I mean, everything is provided. The value for, in order to calculate upthrust, the equation was volume, density, and gravity, right? So you can write upthrust rho v g. So rho is density 998, volume is 5.3 into 10 to the power minus 11, and g is what, 9.81. So if you calculate this, 998, 5.3 to 10 to the power 11. Yeah, that then the final answer you get is 5.188 into 10 to the power minus 7. Uh, is it minus 7? Yeah. So which is almost 5.2 into 10 to the power minus 7, right? So you can write 5.2 into 10 power negative 7 Newton. So we kind of prove that yes, the statement is correct. The upthrust is actually almost about 5 into 10 to the power minus 7 newtons over here. Moving on to the next question. They have provided that the bubble moves upwards at a constant velocity of this much. This is V term. And we need to deduce whether Stokes' law applies onto this bubble or not. You may ignore that the weight of the bubble and the viscosity of the water is also provided. Okay, so for this part, in order for Stokes' law to be applied over here, okay, so for the first law that that has to be fulfilled for Stokes' law to be applied is that upthrust must be equal to the drag force, right? This is drag force. This must be equal to the upthrust. Now, as we have already calculated the value for your upthrust, which was almost 5.2 10 to the power negative 7. So let's find out upthrust. If they are both equal, then yes, then Stokes' laws obviously can be applied to this small bubble. So let's first find out that drag force. The equation for drag force was 6 pi r eta v term, right? The value for v term is given 6 r eta, sorry, 6 pi eta is given for radius. They haven't given anything about the radius. We can actually find out the radius from its volume, which was 5.3 multiplied with 10 to the power negative 11, right? So volume was 5.3 multiplied with 10 to the power of negative 11. Volume, we obviously assume this kind of object is a sphere, so that is 4 by 3 pi r cube, so which is 4 by 3 pi r cube multiplied with 5.3 10 to the power of negative 11. So r would be 5.3 10 to the power negative 11 multiplied with 3 divided with what, 4 pi, and everything under a cube root, right? Okay, so if you calculate it, 5.3 10 to the power of negative 11 multiplied with 3 over 4 pi. So you get 2.33 10 to the power negative 4 as the radius of that bubble. So that's 2.33 into 10 to the power negative 4 meter. Okay, so now you have radius, you have the value for viscosity, velocity, 6 pi. So you can easily calculate the drag force. So F drag is 6 pi r eta v term. So 6 is 6, pi is again pi, r is 2.33 multiplied with 10 to the power negative 4. Eta is 9.5 multiplied with 10 to the power negative 4. And V term was provided as 0.035. So 0.035 over here. All these things are multiplied with each other. So if you multiply it and that will reveal you the final answer. So 6 pi with radius and 9.5 into 10 to the power negative 4 with 0.035 velocity, and you actually get your drag force to be 1.46 into 10 to the power minus 7, which is like clearly smaller than the upthrust. So I'll just write it over here, 1.46 10 to the power of negative 7 Newton, which is basically if drag less than upthrust. So Stokes law certainly doesn't apply to this specific bubble over here, right? So we can write that as if drag is less than upthrust, therefore doesn't apply. Okay, so this was it, the end for your question 16. I hope it was clear for everyone. We'll move on to question 17. The photograph shows a flying object called a buoy. A long chain attaches the buoy to a very large mast at the bottom of the sea so that the buoy remains stationary. And the water flowing past the buoy causes a horizontal force of 260 Newton on the buoy. The chain exerts a force of F on the buoy at an angle of 33 degree to the vertical. So show that F is about 500. Okay, since we have the horizontal forces and over here the buoy actually stays stationary, that means all the forces are actually balanced over here, the object doesn't accelerate, right? As stationary means that the object is at equilibrium, resultant force will be zero, acceleration is zero. So we can write that, we can first draw the components over here. For the horizontal component, we're only interested about that because we only have the other pair of the horizontal component, which is 260. So that is F sine 330 degree, right? So we can write that resultant force equals to 0. For resultant force, what do? You subtract the values because they are in the opposite direction. If they were in the same direction, then you would have simply added together. But they are in the opposite direction, so you subtract them. So you have F sine 33 degrees minus 260 gives you nothing on the other right hand side. So F would be basically 260 over sine 33 degrees. So if you calculate it, that's 260 over sine 33 degrees, and that is 477.4 Newton, which is obviously approximately close to 500. Like if you convert it into one decimal, one significant figure, then yes, this obviously gives you your value in 500 Newton, right? So which is correct. But yeah, other than this, they were also asking you about approximate value, so no need to round it up. That's where we'll stop the maths. Okay, this was it for 16A1. We'll move on to 16A2. The buoy floats due to the upthrust from the water. The weight of the water displaced by the buoy is this much. Determine the weight of the buoy. Okay, now over here again, as the object was at equilibrium, right? So, and in this part, what is actually occurring is that upthrust is acting on this, weight is acting on this, and also a vertical component, right? Which is, as you can see, it will be F cos 33 degree, right? So it basically has three forces acting, which is basically F cos 33, then weight, and then again the upthrust. The weight of the water displaced by the buoy is 2.9. Okay, yeah, it says that the buoy floats due to the upthrust from the water, and the weight of the water displaced by the buoy is 2.9 kilonewton. We need to determine the weight of the buoy over here. Okay, now again, this really doesn't have to do anything with the upthrust over here, because the upthrust was only the force for which the buoy was about to be at the surface of the water, right? What exactly occurs is that this in this situation, all the downward forces must be equal to the weight that has to be displaced by this ball, or by this boy, which was actually over in the water body. So we can write that all the downward forces must be equal to this weight of the water which was displaced by this boy. So on the downward forces we have 477 cos 33 degree, that was F cos 33 degree, and added with the weight of the boy. All this combination of the downward forces was equal to this water weight that was displaced, so which is 2.9 with 10 to the power 3. So weight is basically what, 477 cos 33 minus 2.9 multiplied with 3. So if you subtract all this together, you end up with something 2500 Newton. So that weight of that boy was actually 2500 Newton over here. I hope it was clear for everyone. So we'll move on to the next question, or next part of this question maybe, right? Yeah, the question part B. The speed of the water flowing past the buoy increases as the horizontal force increases. Assume the weight of the water displaced by the buoy does not change. Explain how F and theta would change when the horizontal forces increases. Okay, now over here, if as we already know, what was actually occurring is that this horizontal force was equivalent to the F sine theta, right? So if in this situation horizontal force increases, that means F sine theta is supposed to increase, right? And F sine theta was actually the horizontal component. This is FH, but the F of the vertical component, like the vertical component of this one, would remain same because weight, upthrust, and everything is still the same, right? Weight, upthrust, and drag is still the same. So the vertical component is still same. So what we can do is that we can obviously understand that we can draw a vector diagram out of these three forces. This is the V horizontal, this is the F vertical, and this was the original force. Now as this completely creates a Pythagoras theorem, right angle triangle, so we can use the Pythagoras theorem, which indicates that as the vertical component of the force is constant over here, so which means that if horizontal component increases, the force, the value for F should increase because they are directly proportional, right? And now again, over here, if you have to find out the value for theta, the theta was exactly, the value for theta was exactly like if you have the value for theta over here, that is basically what, vertical over horizontal, right? So in that case, if horizontal increases, the value for vertical is also supposed to increase because they are also directly proportional, right? So I'll just draw it very quickly over here, that at first as weight, upthrust are constant, as weight, upthrust are constant, so you can just write VFV, okay? That is the vertical component of the force that is acceptable in the mark scheme. So you can write, so FV remains same, but we can write due to increase in horizontal force, due to increase in horizontal force, FH increases over here. So if FH increases, so you can now write the equation that F square is equals to FH square plus FV square according to the, like, triangle, right angle triangle that they create. So you can now write, therefore F is directly proportional to FH, so F would increase. Right. Then again, second part, that over here tan theta, or theta, is actually tan inverse FH over FV, which means that theta is also directly proportional to that horizontal component. So you can write theta is also directly proportional to horizontal component, which indicates theta would also increase. Okay, so this is it for question 17. I hope it was clear for everyone. We will move on to question 18. So question 18 says that a student inflates a balloon. She uses a peg to keep the balloon closed. A peg to keep the balloon closed. She then attaches a straw to the balloon using a sticky tape. She passes a string through the straw and pulls the string tight as shown. The student removes the peg and air leaves the balloon. The velocity of the balloon increases from the zero to maximum. Explain how Newton's third law, so three laws of motion apply to this motion of the balloon during this time. Okay, at the very start. As soon as the peg is removed, the balloon is releasing air, right? Which indicates that the balloon exerts a backward force onto the air. Then again, according to Newton's third law, the same amount of magnitude of force will be applied to that balloon by the air, but in the opposite direction, right? So that was the case of your Newton's third law. But again, this force from the air, which is acting on the balloon, acts as a resultant force because now this force is greater than all the resistive forces which was acting on the balloon. So now it has a resultant force in the forward direction, and whenever it has a resultant force, the object will certainly accelerate, right? And whenever the object accelerates, its velocity will certainly increase. That's why its velocity increases from zero to maximum. And again, what happens at the maximum velocity? At maximum velocity, the resultant force again becomes zero, right? So then again, that at maximum velocity, acceleration is zero, so the object reaches the maximum velocity, and it is stated as the maximum velocity because if the object was accelerating, then velocity would keep on increasing, right? So after at whatever stage the acceleration stop, that is what the object's maximum velocity would be. So at maximum velocity, acceleration always has to be zero, and whenever acceleration is zero, resultant force is also zero, right? So we'll just write the answer over here. It is a very common fact or very common question also over here. So we'll start with it, that balloon exerts a backward force onto the air, and then the air will also exert a forward force of equal magnitude on the balloon according to Newton's third law, right? I'll just write N3 over here, but I would suggest not writing N3 in your exams. Write Newton's third law. So now again, as we have quite a lot space and this answer will not take that much space, so I'll make a different paragraph to make it more organized, to make it look more organized. So on the balloon, according to Newton's third law, then again, this force is greater, this forward force on the balloon is greater than all the resistive forces. This forward force is greater than the resistive forces. So there is so according to Newton's third law, there will be a resultant force acting on the balloon. Newton's second law, there will be, according to Newton's second law, there will be a resultant force acting on the balloon. I'm really sorry for my cat. Okay, so according to Newton's second law, there will be a okay. So according to Newton's second law, there will be a resultant force acting on the balloon, and whenever there is a resultant force, the object will accelerate, right? So for which it will accelerate and its velocity increases from zero. Velocity from 0 meters per second. Okay, now again, at the maximum velocity, they also stated that from 0 to maximum, that means you have to state about the fact that what happens at the maximum velocity, why the object reaches maximum velocity. So again, for the last part, at like as speed increases, force also increases, right, until resistive force again becomes equal to this forward force. So we'll write that as speed increases, resistive forces also increases until it becomes equal to the what was it, until it becomes equal to the um, forward force. Okay, so at this point resultant force becomes zero, RF becomes zero, so acceleration also becomes zero, indicating maximum velocity is reached. Is reached. Okay, so this is it for your star mark question of question 18. I hope it was clear. So we'll move on to the question 19. The diagram shows a crane lifting a load that is a large mass called a counterweight attached to the crane to the opposite side of the tower of the load. Okay, so there's a load, there's a counterweight, and this is the tower, and this is the beam overall. The crane is an electric motor with an efficiency of 47%. The crane lifts a load of 4.4 multiplied with 10 to the power 4 Newton. The load moves through a vertical distance of 15 meter in a time of 70 seconds. Determine the average power input of this electric motor. Okay, so over here they have provided you with the force and the distance moved, right? So you can find out the work done, and if you divided it with time, you can find out the output power and how much power was actually used to move the crane. In order to find out the efficiency, determine the average power input. Okay, so now they have already provided you the efficiency, right? So like if you do not have the value for your total power input, that's fine. You can use this efficiency to find out the total power input. So let's find out the power output in general. So power output would be energy over time. Energy is 4.4 multiplied with 10 to the power of 4, then multiplied with 15, this again divided with 70. This will give you the energy, which is 4.4 10 to the power of 4 multiplied with 50 over 70. That gives you almost 9.94285.57. So we can write 9429 approximately newtons. Okay, so this was the power output. We can calculate the power input using the equation for efficiency. For efficiency, value was 47%, which is almost 0.47, right? We can write it like this, obviously. Efficiency is power output over power input is equals to 0.47. Power output was this much you calculated, 9429 over 0.47 is equals to power input. So if you calculate it, you get 20061, which you can write 20061 watt, right? So that is almost a correct answer. It's better to write your answer in like what in standard form, because in that case you can just write your answer in one decimal place, because all the data in your question was provided in two significant figures, so your answer should also be in two significant figures, whereas I kept the answer in five significant figures, which is completely wrong, right? Because the answer can never be more accurate than the data provided. So over here you should write 2.00 multiplied with 4 newton, not newton, watt, right? This was a power calculation. So yeah, this is it. So we'll move on to the next part. I think it was 19b2. The horizontal distances from the load to the tower can be changed. The horizontal distance from the counterweight to the power can also be changed. Okay. Explain how the counterweight needs to move when the load is moved away from the tower. Okay, so over here they were saying that if we were moving the load away from the beam, then how does the counterweight should be moved in order for this to be in equilibrium? So in that case, the first thing that has to be in mind is that the principle for moment, right? The total clockwise moment must be equal to the total anti-clockwise moment, and over here the clockwise moment is only about the weight with the load. So over here, if you are, I mean, we have to state it also that the total anti-clockwise moment is due to the counterweight, and the total clockwise moment is due to the load over here. So if you are moving the load away from the beam, right, as you have stated that when the load is moved away from the tower, if the load is moved away from the tower, they're increasing the distance in between the load and the tower. So as moment only uses force into distance, if distance increases, the overall clockwise moment will increase. So in that case, the anti-clockwise moment should also be increased. And as we cannot change the weight of the counterweight, so in order to find out, or so in order to increase the anti-clockwise moment, counterweight should also be moved further away from the tower, right? In that case, the distance increases, and eventually the anti-clockwise moment will also increase. So we have to write our answer as that total clockwise moment must be equal to the total anti-clockwise moment about the tower. Obviously, about the tower is important point, because even about the tower, center of gravity is working, right? So that is also going to be taken into consideration. So we can write that total, or should be like to be in equilibrium clockwise moment. In this example, the total clockwise moment is due to the counterweight. Here the total clockwise moment is due to and total clockwise moment is due to the load, is due to load. Wait, I actually made a mistake. The clockwise moment was due to the load, and the anti-clockwise moment was due to the counterweight. Okay, so this is supposed to be load, and this is where it's supposed to be counterweight. Okay. Then again, and then and in turn increases the clockwise moment. So therefore, counter should be moved away from the tower. From the tower. Okay. So this was it for question 19b1. We'll move on to question 19b2. The beam is uniform with a weight of 3 into 10 to the power 4. Counterweight has a weight of this much. Load has a weight of this much again. Deduce whether the load will be moved to the end of the beam without the crane toppling. Okay. So if the load is moved at the very end of the beam, in that case, the distance from the tower is 28, right? And and over here, the counterweight is always 8 centimeters or 8 meters away from the tower. So let's find out what the distance would be in that. Okay, sorry, the distance would be 22 because on the other side it was 8. So 30 minus 8 is 22. Okay, so we'll just draw a very simple diagram over here. In order for that like crane to topple, we'll consider that distance, the maximum distance that load can have, can be from the tower is x, right? So we'll just consider that as x. So this is the tower. So the counterweight is 8 meters from the tower. So this is like the counterweight. And I'm assuming that the maximum distance the load can be from that tower is x meters, right? So this is x meters. So this is going to be the load over here. And also another thing, the weight of the beam is acting from the center. So that will be like since the entire length was like 15, so from this part, if this is the center, if this is the weight, in that case this length will be like what, subtract 30 minus 15 minus 8, you get the value, right? That is almost maybe 7 or something. Okay, so that length is 7. So the weight of the beam is 7 centimeters, 7 meter away from the tower. So over here, the weight of the beam and the load is making the beam move in a clockwise direction, and the counterweight is only making the beam move in an anti-clockwise direction, right? So now we can write that momentum, sort of momentum. Sorry, it was supposed to be clockwise moment, anti-clockwise moment. So we'll write clockwise moment is equals to anti-clockwise moment. For clockwise moment, you have weight multiplied with 7. Weight of the beam was 3 into 10 to the power 4 multiplied with 7, and added with the weight of that load was 4.4 into 10 to the power 4. So 4.4 into 10 to the power of 4. This was multiplied with x is equal to weight of that counterweight was 1.1 multiplied with 10 to the power 5, again multiplied with 8. So if you just make x the subject, that is 1.1 10 to the power of 5 multiplied with 8, and then you just subtract that 3 into 10 to the power of 4 with 7 from that 1.1 and divide it with the weight of that load, which is 4.4 multiplied with 10 to the power 4. You can find out the value for your x, the maximum distance that load can be away from the tower, which is I made a mistake, 1.51 into 10 to the power 5 multiplied with 8, then subtract it with 3 into 10 to the power 4 multiplied with 7 over 4.4 multiplied with 4. Okay, so you get the distance to be 15.227. So we can write that x is 15.23 meters. So over here the question was asking to deduce whether the load can be moved to the end of the beam without the crane toppling. Now for the crane to topple, the distance has to be like slightly greater than 15, and at the end of the beam that length would be 22 meters from the tower, right? So we cannot obviously, place that load at the end of the beam, which is 22 meters away from the tower, because that is greater than this maximum distance. And whatever distance that is greater than this this maximum distance of 15.23 is, the crane will topple at that point. Okay, so what if the distance is even 15.5, the crane will topple, right? So we have to write that as maximum distance is less than 22 meter, so crane would topple, right? So crane would topple. Okay, so yeah, this is it for question 19. I hope it was clear. Moving on to question 20. Over here it says that an actor is wearing a harness. The harness is connected to a cable and support as shown. The force on the cable must not cause the material of the cable to reach its yield point. We need to state what is meant by the term yield point of a material. So this is the strain or strain value at like beyond which the object undergoes large plastic deformation, right? So we can write that strain value beyond which object undergoes large plastic deformation. This is more like a definition, so I would expect everyone to memorize it, even though it will not come in this session, right? Because this was the next session exactly. So, still, you can just be sure, get sure of memorizing it. The cable and the harness are used to accelerate the actor vertically off the ground. Explain why the forces acting on the actor causes him to accelerate upward. So this is because that the tension from the cable that is acting on the actor is now greater than his weight. So there is a resultant force in the upward direction. So because of this extra resultant force in the upward direction, object would accelerate in the upward direction, right? According to Newton's second law. So we can write that the tension in cable is greater than the weight of the actor. So there's a resultant force in the upward direction. RF in the upward direction which causes him to accelerate. Okay. So yeah, that is it for question 20B1. We'll move on to the next part. The actor has a mass of 77 kg lifted vertically from the ground with an acceleration of 2.7. Show that the tension in the cable is about 290. So over here, if I draw a free body force diagram, only weight in the downward direction, that was 77 g, and in the upward direction it was only tension. So we can write that resultant force is equals to mass acceleration, or the resultant forces will be what? Tension minus weight, 77 g is equals to 77 or multiplied with 2.1, because the acceleration was 2.1, right? So this is how the equation looks like. So it will be 77 multiplied with 2.1 and then added with 77 multiplied with 9.81. So if we calculate this, you get 917 Newton, which is approximately 920, but you could just write 917 because they also are talking about approximate values. Okay. So to make sure that the actor is safe, the stress in the cable must be less than 15% of the yield stress point. The cable has a yield stress point of this much. The diameter of the cable is this. And if the diameter is this, then the radius would be half of it, right? So 7.3 over half. So 7.6 over 2 is basically 3.8 10 to the power 8. We have 7.6 10 to the power minus 3, and this divided by 2 is basically 3.8 to the power of 10 to the power of 3, so which is 3.8 10 to the power of minus 3 radius meter. This is the radius of that area of that cross-sectional area of that cable. We need to determine that whether it is safe to lift the actor with an acceleration of 2.1 or not. Okay, so over here, in order to identify that, we have to first find out that if the amount of stress over here is actually less than the 15% of that yield point stress or not. So for that stress, we have that force, right? At 2.1, the force was in the tension force was 917 in that case. So as we're only talking about that cable, so we're just going to deal with the 970 Newton tension force in the cable, not the force of the actor or the weight of the actor. Okay, so we have in order to find out the stress over here, force over area is the formula, where force is the tension 917, area is pi. We also found out the r, that is 3.8, right? So that is 3.8 10 to the power minus 3. So this is pi r square. So we calculated 9.1, so 917 over pi into 3.8 with 10 to the power minus 3 square. You get 20, 21 zeros. Okay, that's a very large value, so I'll use standard form 1, 2, 3, 4, 5, 6, 7. Okay, so you get 2.02 into 10 to the power 7. Okay, as you can see, this was the stress that was actually in that in that cable, right? So if you have to find out that 15% of it, so that will be sorry, 15% of this so the yield point is 2.7, 2.5, right? So first find out that 15% of 2.7, like how much is actually 15% of 2.5 when you 10 to the power 8 is actually, right? Because your stress in the cable should be less than 15% of the yield point. So find out how much value of stress is actually 15% of the yield point actually indicate. So we can write that 15% of yield point is of yp is actually 15 over 100 multiplied with 2.5 into 10 to the power 8, and you get 3.75 multiplied with 10 to the power 7 pascals. So if your stress in the cable is less than this value, then it is safe to use. And we can clearly see that 2.02 multiplied with 10 to the power 7 is certainly less than 3.75 multiplied with 10 to the power 7, therefore safe to use. Okay, so this was it for question, I think it was 20B3. So we'll move on to this next page, the last question. Okay, the original cable is replaced with a new cable made from a different material. The material is has a lower Young modulus than the material used to make the original cable. Okay, So the new material has a lower Young modulus, and the new cable is the same length as the original cable but has a greater diameter, so which means that radius is higher for the new cable, and the breaking stress is the same for both cables. Okay, explain how the work done to break the new cable is different from the work done to break the original cable. Assume that both materials obey Hooke's law up to the breaking point. Over here, if you focus on that like diameter, it indicates about the radius, and again it indicates about the area, right? So if you focus um, um, wait work done over here, right? So for work done, we actually use the equation work done. Wait, okay, let's just write the equation for Young modulus stress and strain. For Young modulus stress and strain, this equation is actually force over um, length multiplied with area with extension, right? So since the area is increased and Young modulus is decreased, that means like in this situation, if you just make force the subject of this equation, right, in that situation the equation like in the entire case, the formula would be Young modulus over area delta x over length. Since length is same for both the old and new wire, so length will not be a factor. And the area and the Young modulus is a factor over here. If the cross-sectional area is greater, right? So now it will obviously require a greater force because area and force are directly proportional. Now again, if the new wire has a smaller Young modulus, for Young modulus, you can clearly see from this part, yeah, for Young modulus and extension are inversely proportional. So now again, for smaller Young modulus, they will have a greater extension, right? For a very smaller Young modulus, there will be a greater strain for the same stress. So now this entire cable will actually like come to the breaking stress at a greater extension because the lengths were both same for the old and new. So the 3 points over here, wait, so there are 4 points, right? Yeah, but like finally, as both force and extension increases, so what means work done to break this entire new cable is farther greater than to the original cable. So over here, the first mark is about the diameter. For a greater cross-sectional area, more force is required, right? Because like now, obviously, it has it has to maintain the same formula, right? So force area, like force and area, are directly proportional. For a greater area, forced must increase. So we will write that for a greater area, for a greater cross-sectional area should be a better word. For a greater cross-sectional area, a greater force will be required. Is required. Okay. Now again, in this situation, for obviously a greater force is required. Again, about the fact that the new cable has smaller Young modulus, so there will be a greater strain for the same stress, right? I'll just write Young modulus as YM even though it's not accepted in the mark scheme. So as new cable has stronger Young modulus, so smaller Young modulus, there will be a greater strain, which means that a greater extension over here, right? So the breaking, so there will be a greater extension, a greater extension as delta x is equals to Young modulus dot L. If L is constant and if strain is increasing, so obviously delta x is also supposed to increase because they are directly proportional, right? So we'll write that as length is same. Okay, now later on, if if both delta x, like extension, is increasing, force is increasing, then obviously work done in order to break that new cable is further greater than that of that original cable, right? So we can write that an extension, delta x represents extension. So as force and extension increases, would also increase. Okay, yeah. So this is it for the entire paper of June 2023, Unit 1. I hope it was clear for everyone, and thank you for watching.